Hello, my name is Marcus Kjellander from Noah's Ark lab at Huawei. I will shortly present mine and my coworker Sisha's approach for the KDD Cup multi-dataset time series anomaly detection competition. And in the competition, we participated using the team name Old Captain. So our solution is an ensemble method where a diverse set of algorithms are applied to get the final prediction for the anomaly location. The algorithms are applied in a predetermined order until one of them is confident enough in its prediction, in which case the prediction is used in a winner-takes-it-all fashion. So what we actually do is shown in the diagram here. We start by applying the first algorithm on a time series, and each point is given an anomaly score. From these anomaly scores, we compute a confidence C, which is compared to an algorithm-specific threshold T. And if this confidence is above the threshold, then we consider the prediction to be confident, and we return the location with the highest anomaly score. However, if the prediction is not confident enough, then we continue by applying the next algorithm. And in the event that all algorithms have already been tried, then we use the algorithms whose confidence level is relatively closest to its threshold. And the reason for this approach is that we've found that as long as an appropriate algorithm is used on a time series, then the anomaly location is often quite obvious. And using this strategy, we can have a set of algorithms that each are focused on a specific anomaly type or focused on a time series with some particular characteristic. So there are a few key components for our solution to work. So the first one is we need a way to measure the confidence level of an algorithm. And I will introduce our approach on the next slide. Other than that, there are two more components that we heavily rely on. And the first of these is the period inference, where we infer the seasonality of the time series using the fast Fourier transform method. And we base most of the method-specific parameters on the length of the inferred period, such as the window size for smoothing, etc. And this is mainly for simplicity reasons, but it also has the advantage that two time series with the same shape but different sampling rates are treated the same. The other component is ensemble learning. So some methods are more sensitive to proper parameters, so we added ensembling to these to try different values. And we focused on applying different multipliers to the inferred period, since this is used as a base for most parameters. But there are also other things such as whether to normalize the data or not. So to understand the period multipliers, we have an example here with a time series T and an inferred period of 12. And we have three multipliers, 0.5, 1, and 2. So we then run this method with three different periods, 6, 12, and 24. And then we select the result with the highest confidence score. So for the confidence level, we use a general method that can be applied on any algorithm. So we compute the difference between the maximum anomaly score and the second largest score. And here we exclude any anomaly scores within the same peaks. So this value 9.6 here is ignored. Then if this difference is above the specific threshold for this algorithm, then we return the location with the maximum anomaly score as our anomaly prediction. Of course, here we also need to check if the maximum score is within the training partition of the data, in which case we won't use the prediction. So in this case, the applied method is considered unsuitable for the considered time series. It's also relevant to note that by adjusting this acceptance threshold, we can regulate how conservative an algorithm is. And this is the list of all the base algorithms that we used in the final version in the order that they are applied. So it's a total of 11 different algorithms, but some of them have some similarities. There's two different versions of STL decomposition-based methods, and there are 4 different versions that uses the matrix profile in some way. So as I said, the order of the applied algorithms are relevant to our solution. So we want the more conservative methods to be run first. If these methods are confident in their prediction, then we want to be very sure that the prediction is actually correct. Otherwise, we would want any of the later algorithms to be used instead. So overall, the acceptance threshold for the earlier methods is higher than for the later ones. So the first 3-4 methods here requires a confidence level of about 3, while the later ones only have a threshold of around 0.2 or so. The order of the algorithms also consider the relatively difficulty of the anomaly types that these algorithms are focused on. So any obvious anomalies should be found by the first few algorithms, and that allows the later algorithms to be more specialized in finding more complex anomalies. The order added column here shows the general evolution of the solution. So this is an iterative process where we tried out different methods and saw which time series they performed well on, and then we try to focus on the ones without confident predictions. So there's not enough time to go into details of each algorithm, but I will shortly mention some key ideas behind some of them. So for the first one here, discrete, it focuses on time series with a few discrete states of different lengths. So these type of time series can easily be found since they only contain a few unique values. What we then do is we look at the change in the states to see if there are any unique changes that only appear in the test partition of the data. We also have, for example, this variance ensemble. It tries to find areas with abnormal variance in a sliding window, and it considered both high variance and low variances. Here we have an ensemble over different window lengths and whether different pre-processing steps should be used or not. We also have something called flat that finds relatively flat, non-smooth connected sections in the time series, and STL decomposition that's focused on finding abnormal spikes in the time series. Then for shape-based anomalies, I've chosen to mainly rely on matrix profile and to analyze its discords. So to summarize, our solution is based on an ordered expert ensemble, which applies a list of anomaly detection algorithms in a specified order until one of them makes a confident prediction. And the confidence is measured by comparing the top anomaly score with the second highest scores. We use a diverse set of algorithms that specialize in finding different types of anomalies. And the order of the algorithms is dependent on their conservativeness and thus also conditional on this threshold. And the idea here is that the first algorithm should make the most conservative predictions. And the acceptance threshold parameter is key to a good performance here. So that's all from me. Thank you very much for your attention.